In this video, I would like to introduce you to the idea of limit by starting with the graphs of a few familiar functions. So I'm asked to graph y equals x, y equals sine of x, y equals 2x over x minus 1, and y equals x squared minus 9 over 3. Y equals x, every time I plug in a value of x, I get out the same y, and I get this nice happy line. To graph sine, I need to remember that sine starts at 0 and then waves between 1 and minus 1. I have my x-axis here labeled in pi halves. That might not be showing up very well in the video, but I'm always going to label at least 5 key points on every period of a sine or a cosine graph. So here are 2 periods of y equals sine x. And here I have 2 rational functions to deal with. So I thought we would take a moment to review how to graph a rational function. To graph a rational function, I take my rational function, I think of it as a polynomial over a polynomial. And if that rational function is lowest terms, my steps are pretty easy. The vertical asymptotes occur where the bottom is equal to 0. The x-intercepts occur where the top's equal to 0. Because anywhere the top's equal to 0, 0 divided by a number is 0, I get an x-intercept. For the y-intercepts, I just plug 0 in for x. And then for the horizontal asymptotes, I need to remember 3 rules. And those 3 rules are, if the degree of the numerator and denominator are the same, then I take the quotient of the leading coefficients, and then that's my horizontal asymptote. If the degree of the bottom is larger, then my horizontal asymptote is at y equals 0. And if the degree of the top is larger, then there is no horizontal asymptote. We'll see 2 of those rules come into play in our examples. All right, so this first rational function, 2x over x minus 1, they do not share any common factors, so they are in lowest terms. So I can just follow the things that we just went over. The vertical asymptote is going to be where the bottom is equal to 0. So the vertical asymptote is going to be at x equals 1. For the x-intercepts, I need to set the top equal to 0. And I find out that the only x-intercept is at x equals 0. Well, if I think about plugging 0 in for x, I'm also going to get that, and that's good because that's on the x-axis and the y-axis. It's both intercepts. And then for my horizontal asymptote, the top has degree 1, the bottom has degree 1. The horizontal asymptote is going to be y equals the quotient of the leading coefficients. 2 over 1 is 2. In this class and in any math class as you go forward, when you write down asymptotes, they should always be equations. The horizontal asymptote is the vertical line, the horizontal asymptote is the horizontal line, y equals 2. The vertical asymptote is the vertical line, x equals 1. Always write those as equations of lines. All right, so now I want to finish my graph. I'm pretty sure I know what this graph looks like. On this side, getting closer and closer to my asymptotes. On this side, let's think about plugging in 2. 2 times 2 is 4. Over 1 is 1, so 1, 2, 3, 4, and then my graph will move towards my asymptotes. A nice, happy, rational function. So when I look at this rational function, I have x squared minus 9 over x minus 3, and I realize that right now, the rules as I have written them do not apply, because this rational function is not in lowest terms. There's a common factor to worry about. The top is x plus 3 times x minus 3. I can think about canceling off the x minus 3's. In this function I started with, x squared minus 9 over x minus 3 is going to look like x plus 3 everywhere except x equals 3. Because x equals 3 is not in the domain of this function. It's never going to be in the domain of this function. So let's graph this line, now that I have it in lowest terms, and see what I think might be happening at x equals 3. So x plus 3 is a nice happy line. It has a y-intercept at 3. The slope's 1, and I could plot more points. But I think my graph should look something like this. With one problem. Right now, it looks like if I plug in 3, I should get out 6. But I can't plug 3 into my original function, so I just come up here and I say, nope, that's not in my domain. And that's what I remember about those common factors from my pre-calculus class. Where I have factors that cancel, I get holes in the graph. So that gives me two different ways of thinking about what happens when the bottom is equal to 0. I either get a vertical asymptote or I get a hole in the graph. So those are just 4 functions that you might have graphed in a pre-calculus class. I want to think about a function that will come up in this class quite a lot, hopefully motivating an idea, a new idea, an idea of limit. So what I want to do now is graph f of x equals sine x over x. And I want to use the things we've been thinking about so far. It's not a rational function, but my intuition might be that there might be a vertical asymptote or a hole where the bottom's equal to 0, that there might be x-intercepts where the top's equal to 0, and I should be able to find the y-intercept by plugging 0 in for x, if there is one, and if there's going to be a horizontal asymptote, maybe something along the reasoning of these 3 rules will work. So, we're going to use that kind of logic to graph this particular function. Let's start by thinking about the x-intercepts. Since I have a sine involved, I'm just going to split up my x-axis in my usual way. I'm running out of room here. That's going to be okay. I'm just going to sneak a minus 2 pi right there. And I know that I'll have an x-intercept anywhere the top's equal to 0, except for maybe where these things are 0 at the same time. Because that's what happened on this function. Where the top and bottom were 0 at the same time, I got a hole. So when I look at this, sine is equal to 0 anywhere its graph had an x-intercept. So I know where my x-intercepts for this graph will be. The only one I have to be worried about is at 0, because sine of 0 is 0, and plugging 0 in for x on the bottom will give me a 0. So these x-intercepts I'm sure about. Pi, 2 pi, minus pi, and minus 2 pi. But I don't know what's going to happen at x equals 0. So let's see if we can learn more about this graph a very old-fashioned way, just by plotting some points. When learning about a function for the first time and exploring it, it's always all right just to imagine what happens when you plot a few points. So I just want to plug in a few points to the sine function. And so I've picked pi halves and minus pi halves right here just to try to get some idea of what's going on. Well, if I plug pi halves into sine, I would get 1. Sine of pi halves is 1. On the bottom, I would get pi over 2, and that's actually going to end up being 2 over pi. So 2 divided by 3.14159 something something. I'm going to imagine that to be just about right there. I'm going to imagine it to be somewhere just beneath 2/3. Plug in a minus pi halves, and you're going to get a minus 1 on the top and a minus pi halves on the bottom. You're going to get that same value at 2 over pi. And so if I think about it, as x gets bigger, the bottom's going bigger, and the sine function's trying to just go back to 0. So I think I know what's going to happen. This is going to go to that x-intercept, and this is going to go downwards towards that x-intercept. And so now let's plug in 3 pi halves and minus 3 pi halves. And I think I know what's going to happen, but let's be sure. So if I just imagine plugging in 3 pi halves to sine, I get minus 1. So that'd be minus 1 over 3 pi halves. So I get the reciprocal, the opposite reciprocal. And so it's negative and it's smaller. And so whatever this function is doing, it seems to be waving. And I think it's going to keep doing that wave because sine's always going to bounce between 1 and minus 1. And as x gets bigger, the bottom's just going to get bigger and bigger. So I think it's going to keep waving, but by less and less and less. And the same thing's going to happen over here. If you were approaching a problem like this, I think decimal approximations from your calculator would be fine, but this is a nice function just to evaluate things. And so the only place I'm still kind of curious about is what happens when the x values get really, really close to 0. Because I promise you the domain of this function does not include 0. I can't include 0 in the domain because I'd be dividing by 0. So here's a question. What happens to the y values when x is close to 0? But not actually 0. So, I want to know what's happening when my x values get close to 0. What are the y values doing? So let's see if we can build a table of values to help us with that. So this will be my table helping me explore what happens when x gets closer and closer to 0 without actually getting there. So I'm just going to pick numbers that get closer and closer to 0 from both sides. And this time I do think I'll use my graphing calculator to help us out. So, I'm going to take my handy dandy TI-83. And because I'm dealing with a trig function here, I want to make sure I'm in the radian mode. I had to put my calculator back in the function mode because apparently I had graphed a parametric equation previously. But here, dealing with a sine of x, we want to be in the radian mode. We're going to hit y equals, and I'm going to type in sine of x divided by x. And I had to get my parentheses in there so I actually was graphing the right function. And I'm going to hit second window because I really don't care where the table starts, but I want it to ask me the independent variable because that's going to let me type in the ones I want without having to scroll through a table or have it do weird things. And now I'm hit second graph to get into the table menu. So minus 1 goes into the sine function, and I get about 0.8. Minus half, and I get 0.96 if I round correctly. Being a little carefree with my rounding, because I'm just trying to figure out what's going on here. All right, and I think I see what's going on. So minus 1 would be about right here. And that's about 0.8. And as I get closer and closer to 0 here from the left-hand side, it looks like I keep getting closer and closer to 1. On this side, I'm actually going to see those same values because sine x and x are both odd functions, and an odd function divided by an odd function is an odd function. But if I just type them in really quickly, you're going to see those same values occur over again. And I don't have room to type in the 1. We could put it somewhere else, but we're going to get that same value. So I'm just going to fill these in kind of quickly. And what I see is these would get closer and closer to 1. And if I got even closer, so I think there's a hole there. just like in that last rational function. As x gets really, really close to 0 without getting there, the y values are also getting close to 0. So what I would claim here is that we've discovered in this function, as the x values get really, really close to 0 without actually getting there, the y values get super close to 1. This is what we actually mean in mathematics when we say limit. We would usually write it down like this. The limit as x approaches 0 of this function f of x equals 1. When I see this statement, what it's saying is, hey, when the x values get really close to 0 without ever getting there, the y values are getting closer to 1. In the next video, I'm going to write down what I would think of as an informal definition of limit. But this idea of limit is always going to give us the way to interpret, a way to interpret what's going on. What happens to the y values when the x values get super close to something without actually getting there? All right, so there's your introduction to limits using a few common functions. Bye for now.